continuing from where we left off. Sorry, I didn't realize the video was about to cut off on me. But we were trying to find the noble gas notation for gallium, and we had just talked about how you need to find the noble gas on the row above where your element is located. And so the noble gases are all in the far right column, and argon is the element that's the noble gas on the third row. So that will take the place of the electron configuration all the way from the 1s up through the 3p6, because that is the whole, all the way up through the third energy level. And so the only part of the electron configuration that we still need to write in noble gas notation is everything that is on the last energy level. So just the 4s2, 3d10, 4p1. So to finish out our noble gas notation, we'll have 4s2, 3d10, and 4p1. So this is kind of like abbreviation of the electron configuration. Okay, so now let's try this for chlorine. Actually, I'm going to bring chlorine down here since we're running out of space. Chlorine, if you look at your periodic table, is located on the third row in the 7th column, or the 7th group, towards the right. So that means that we need to use the noble gas from the second row. So look up to the second row, and all the way to the right, you will find neon. Okay, neon will be the noble gas that we write, and then we're only going to write the third row for the electron configuration until we get to chlorine. So that'll be 3s2 if you look over at the left, and then move across to the right, we see the p block up until 1, 2, 3, 4, 5, we get to chlorine. So 3p5. So this would be the noble gas notation for chlorine. And then finally we have strontium. Now normally, since strontium's on the 5th row, it would have a pretty long electron configuration, but we can shorten this very easily in noble gas notation. So let's look, we're on the 5th row, we got to go up to the 4th row and all the way to the right, and we'll find krypton is the noble gas that comes before strontium. So I'll put that in brackets, and that's summarizing the 1st through 4th energy levels of our noble gas notation. And then strontium, the element we're actually looking for, is in the 5th row in the 2nd column. So that means it's in our 5s sublevel. So I'm just going to write 5s, and then it's the second element over in the 5s, so that means there are 2 electrons in the 5s. And then we're done. We have the noble gas notation for strontium. All right. Okay, so Hund's rule has some interesting exceptions that happen that will cause us to have to change how we wrote our orbital notation or electron configuration. And it's going to be a little easier for us to see this in orbital notation. But Hund's rule was saying that we need to put 1 electron in each orbital before pairing them up. So the cases in which you'll see a strange occurrence is when there are 2 electrons in the p orbital. So let's look at your periodic table to the p block and count 2 elements over from boron to carbon. That whole column where carbon is written is going to have this weird thing happen. And so right below carbon you'll find silicon, and that's why we're going to use silicon as an example of this. When we write out the orbital notation, let's just do this for the 3rd energy level, pretending like we did the noble gas notation. So neon was the noble gas that came before silicon, and then we have the 3s level, which in orbital notation we just draw that 3s orbital, and then we have 3p, and there are 3 orbitals for 3p. So if we're going all the way over to silicon, we know that we have the 2 electrons that would be in the s, but then we also have 2 electrons in p. So I'm going to put 1 in each of the first 2 orbitals, and that gives us all the way up to silicon. Okay, so let's read what it says. When there are 2 electrons in p, s electron moves up to the p orbital. So you see how we have this empty p orbital. Okay? The electrons really would prefer to be by themselves because they have more space to move around and they have a lot of energy, so they move around a lot. And if there's two electrons in one orbital, they feel a little bit cramped. That's one way to explain it. That's not actually what's happening, but it's one way to think about it. So since there's two paired up over here in my S, I can take one of these electrons and I can move it over to that available orbital. So my final electron configuration or orbital notation, I would write it like this, where there's one electron in the 3s and 3 electrons in the 3p. So if I change this to electron configuration, we would have 3s1, 3p3. Okay? So this is the true official way to write electron configuration when there are elements in the 2p or in the p block 2 electrons over. So carbon down through lead. This is the real way that you would write their electron configurations for the valence electrons. Okay, so the same thing is true when we're in the D block. If an element has 4 or 9 electrons in the D block, one of the S electrons can move up. So let me show you what I mean by that. So chromium is located on the 4th row in the 3D sublevel. So the noble gas that came before that was argon, and then we have 4s2, 3d4. Okay, so I'm going to write out these orbitals. So we had that 4s, and there were 2 electrons there, and then we have 3d with 5 orbitals, and there are 4 electrons. Put them each in separate orbitals. And then we have this lovely empty space that would like to take one of the S electrons. So I'm going to take one of my S electrons and move it up here to my empty 3D orbital. So this will become 4s with 1 electron, and 3D will have its 5 separate orbitals, 1 electron each. And now the electrons have more space to move around, and that's optimal for the atom. Okay, the same thing will happen, and this is the strange case, when there are 9 electrons in the D. So an example of that is copper. Copper is in the 9th spot on the 3rd row for the D block, and so this will have the same thing, argon with 4s2, 3d9. Okay, I forgot to change this to electron configuration over here. This would be 4s2, or 4s1, 3d5. That's the official electron configuration for this. Okay, so if we go back to copper here, we have 4s2, 3d9. So that S orbital would normally have 2 electrons in it, and then we have the 3d 5 orbitals for that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the strange thing, but for some reason the S electron is more likely to be by itself than for there to be an empty spot in the D orbital. So one of these S electrons again will jump up to the D orbital. So the new orbital notation will be, this is 4s, and then 1, 2, 3, 4, 5. This is 3d. And now these are all full. And 10 here. So that means my electron configuration will be 4s1, 3d10. Okay, so this is a little odd, but this is actually what happens in this can be verified with experimental data. So this is how you would actually write the electron configuration for these elements that fall into those columns on the periodic table. And that's all we have for today.